organized by the Department of Mechanical Engineering, Jyoti Engineering College, sponsored by ATAL Academy, New Delhi. Today, we are privileged to have with us Dr. P. Biji as the resource person. Dr. P. Biji completed her MSc degree from Cochin University of Science and Technology and PhD degree from Indian Institute of Technology, Madras. She has nearly 12 years of working experience, which include both teaching and research. Currently, she is working as Associate Professor in Nanotechnology, PSG Institute of Advanced Studies, Coimbatore. Dr. Biji has qualified graduate aptitude test in engineering and national eligibility test. She bears life membership in many professional associations, including Material Research Society of India, Institute for Smart Structures and Systems, and Indian Society of Systems for Science and Engineering. She has guided 6 PhD and 2 MPhil scholars and currently guiding 6 PhD scholars. Dr. Biji has executed many funded and consultancy projects funded by various agencies, including Department of Science and Technology, Indira Gandhi Center for Atomic Research, Defense Research and Development Organization, National Program on Micro and Smart Systems, Oil and Natural Gas Corporation, Aeronautics Research and Development Board, etc. She has published several research articles in peer-reviewed international journals, national and international conferences. Her area of interest include gas sensors and ion selective sensors, super hydrophobic coatings for solar panels, and clean energy materials. On behalf of the Department of Mechanical Engineering, Jyoti Engineering College, we extend our heartiest welcome to you, ma'am. Please continue with your presentation, ma'am.
Thank you, Dr. Deepan Raj. So I will start sharing my presentation right now. 1 second. Can you see?
Yes, ma'am. It is visible.
Can you see the first slide?
Yes, ma'am. It is clear.
Thank you. Good morning, everyone. First of all, I would like to thank the organizers of this FDP on solar energy technologies and applications. Thank you very much, Dr. Deepan Raj, for introducing me. And before going to the talk, I would like to introduce our institute where I am working. I think PSD College of Technology, everyone will be familiar with, but I am working in the same campus. The institute name is PSD Institute of Advanced Studies, Coimbatore. So this institute started in 2006 by PSD Management, which is located inside PSD College of Technology, main campus, Vilameda. Basically, this is a nanotechnology research center with the state-of-art facilities for nano-characterization and nano-fabrication technologies. So we have almost all facilities like for nano-characterization, like HRTM, SCM, AFM, confocal Raman, then clean room microfabrication facilities like PVD, ICP, CVD, maskless lithography techniques, etc. And then if you want to know more about our institute, you can visit our website, which is given here, pstias.ac.in. And of course, it is open to external users. So if anyone wish to use our facility, kindly contact us. So now coming to our my research activities, my group is mainly working on sensors and clean energy materials. So since this FDP focus majorly on the solar energy, I would like to discuss about one of the activities which we are doing in this particular field. So although I don't consider myself as a great solar energy expert, of course, we are looking into some nanotechnology solutions for few challenges faced by the existing silicon solar cell solar energy technologies. So in this area, my group is working on 2 projects which is supported by a DST and ONGC Energy Center. With ONGC, of course, we were developing some self-cleaning coatings for solar panels to reduce the soiling issues in of the PV installations. So that's a major project which is still going on, as a consecutive projects. So I may not discuss on that topic today because time may not be sufficient. So I would like to discuss on the second area, which is the advanced front contact grid metallization for silicon solar cells. So as I told before, I will not talk anything about the basic solar cell operations and principles today, because I hope your previous speakers would have already covered all such important aspects. So I'm interested only on the front contact metallization, and we will see how can we improve the solar cell efficiency with our approach. Solar energy is slowly becoming the part of our life, significantly in the event of serious threats of global warming and to meet our increasing energy demands. The reason behind the global warming, of course, is caused by several reasons, and especially the increased concentrations of greenhouse gases in the atmosphere, mainly arise through the anthropological activities like burning fuels, fossil fuels, then deforestation and agriculture, which is again linked to serious environmental climatic threats, like we are witnessing many droughts, then floods are coming every year in various parts of the country as well as globally, and more powerful hurricanes, then melting of polar ice, etc. All these kind of dangers we are encountering, which actually endanger the existence of life in this planet. So approximately, we can see that around 1 degree Celsius increase in the average global temperature is reported since 1880. So the below this chart shows the percentage share of contributions of carbon dioxide emissions from various sources in different countries. So majorly the main source of carbon dioxide or greenhouse gas emission is produced by the production of electricity and burning of fossil fuels or coal for various industrial and electricity applications. So the major culprit, of course, is fossil fuels, which is also depleting at a very faster rate at present. So obviously, we have started thinking about the alternate renewable technologies in order to reduce impact of global warming. As you know, the population also is increasing, and hence our energy demand also is increasing. So although non-renewable energy sources like coal, oil, gas, or even nuclear power, we are using to meet our current energy demands, such resources, however, are not sustainable forever. So globally, there's a huge movement has started towards renewable energy resources, such as solar power, wind, hydromass, tidal power, biofuel, etc. So how nowadays we have also started using hydrogen as a clean energy fuel, which can be produced from electrolysis of water using solar energy also. So next slide, yeah. So now our government of India has started a huge ambitious target of installing 175 gigawatt of renewable energy capacity by the year of 2022, which includes 100 gigawatts from solar, 60 gigawatts from wind, 10 gigawatts from biopower, then 5 gigawatts from small hydropower. So the government also has, we already know, the government has launched several schemes for the promotion and the development of renewable energy, including solar energy in the country from time to time. But at present, India's total installed capacity is around 632 gigawatts, with the renewable energy constituting up to around 23%. Considering the renewable energy contribution at present, wind energy is dominating as a 10%, followed by solar energy, which is up to 9%. But unfortunately, this particular chart is the data from 2019. So in the year of 2020 June, we have reached up to 37 gigawatts from the solar power, which means that we would have crossed the wind contribution by solar energy. So I think you must be familiar with this NREL efficiency chart. So from this latest chart, we can understand that the solar cells have reached almost up to 47% by NREL. Whereas, but unfortunately, such high efficiency solar cells are highly costly. So at present, it has not come to, I mean, of course, it is using for some other application, but not widely popular. So if you see the popular solar cell technologies, of course, our silicon solar cell, which is mature technology right now. So the maximum efficiency reported by silicon solar cell is up to 27.6%. But of course, when you see the commercial solar cells, it's maybe in the range of 18 to 20% only we will be getting. So now let's see very briefly the silicon solar cell manufacturing process flow. So at first, what's happening is from the silica, silica is the source of the silicon. So silica sand is initially purified to up to 100% or 99% of silicon using carbon arc welding curve process. We call it as curve process. So the silicon is further refined to become almost 100% pure. Then further this silicon is doped because we need to get the PN junction. So the silicon will be doped as a P-type or N-type using boron or phosphorus. And further the silicon is extracted into an ingot using Soralsky process. So the round ingot is a diamond wire cut into a very thin slices of square wafers. Then further the wafers are coated with a thin layer of either P or N type silicon to form the PN junction. So that's the solar cell. So after that, we need the anti-reflecting coatings. So the anti-reflective coatings are deposited and further the metallic fingers, because the current collection has to happen. So you need the metallization. So the metallic fingers are deposited on the top, and the rear contact will be fabricated after that. Then further the flat ribbons bus or something where bus are added. So that's how the solar module is manufactured in the industry, and which will be further integrated with the inverter, and it can be used for either domestic or industrial applications. So at present, there are several types of silicon solar cells has been invented. So some of the examples are like PERC or Pearl solar cell, bifacial cell with passivated diffusion at the rear. That's called as a Pasha cell. Then interdigitated back contact or IBC solar cell. Then of course the silicon heterojunction solar cell. So such kind of various modifications in the structure has been achieved right now. So I don't want to go to the details of such different types of solar cells, because we need some time for our main topic. So then again, let's see also this solar cell manufacturing process flow in a little detail. So once the wafer has been formed, so there are several steps involved. So the first step is pre-check, or we need the pre-treatment. So at this stage, the raw silicon wafer first undergo a pre-check. Then during which they are inspected on their geometric shape or thickness anomalies. And some damages like cracks or breakages or scratches are present on the wafers. Then further, after the pre-check or pre-treatment process, then texturing happens, texturing and cleaning. So following the pre-check, the front surface of the silicon wafers are textured to reduce basically it is to reduce the reflection loss. of the incident light. So the most common technique is the random pyramidal texturing. Then after that, after texturing, this wafers undergo an acid cleaning. So in this step, any post-texturing particles remains on the wafer are removed from the surface because next stage is a diffusion. So diffusion is basically the doping. So it's basically to make the silicon wafer to more electrically conductive. So there are two methods for diffusion. First one is a solid state diffusion and the emitter diffusion. Then after this diffusion process, the next stage is the etching, isolation, and cleaning. So during diffusion, of course, the N-type of phosphorus will be diffusing not only on the desired wafer surface, on the front surface, but also at the edges of the wafer also. On the back side also. So this will create actually some kind of electrical path between the front and the back side contacts. So in this way, that may prevent the electrical isolation between both sides. So objective of this particular step, the etching and the edge isolation, is to remove this particular electrical path. So after that, the ARC deposition. ARC is the anti-reflective coating. So after washing, these wafers can further be processed for deposition of ARC coating. So thin film of silicon nitride, basically. Silicon nitride is commonly used. Of course, titanium dioxide also is used in some cases. But most common ARC coating is a silicon nitride coating. So at that stage, the color of the solar cell will be changing by varying the thickness of the ARC coating. So if you see the solar cell, silicon solar cell, almost everything will be in blue shades. So different shades of blue will be appeared. So that means that the thickness of this ARC coating, the silicon nitride thin film, is varying. So depending on that color only, they categorize or cell sorting will be happening. Then further, the next important process is the contact printing, because we have constructed the solar cell now. So now what we need, the current has to be collected from this photoelectric effect. So the metallization happens through silver screen printing. The most commonly used technology is the silver screen printing. So after printing of this silver paste in appropriate dimensions, depending on their design, then sintering happens. So during sintering, it actually being contact with the emitter layer, and further the cell testing and the cell sorting happens. So now, having understood about this manufacturing of the solar cell, so now let's slowly come to our topic, the why this metallization is so important. So I want to give you some basic introduction. So this is basically to reduce the optical losses. So losses in solar cell occurs in two different ways. One is the optical loss, and second one is the electrical loss. So electrical loss, basically it is the ohmic type or ohmic losses or the recombination losses. So that's these two losses basically depend on the materials which are used in the silicon solar cell. So I don't want to explain more about this kind of electrical losses right now. So I want to concentrate on the optical loss. So the optical loss, basically it happens from the reflection loss, then shadow loss, or some radiation, the photon which will not have absorbed in the solar cell. So because of that, some parasitic absorption, parasitic reflection happens. So that also contributes towards the loss, optical loss. So let's see more about this. So basically, I have the first figure, which is a AM 1.5 solar spectrum, which is represented in that gray shade. So we can understand that the entire spectrum is not available by the silicon solar cell. So that red region, the red region which I have shown here, is the available energy which can be utilized for by silicon solar cell after consideration of the thermalization loss or transmission loss. But again, this is a kind of a theoretical maximum which we have represented. So the actually, when you see the commercial solar cells coming around the 23 or 20%, so you are not actually getting the benefit of the entire spectrum, which is shown in this red region. But actually, what you are getting is this purple color, which I have shown in the second spectra. So that's a current limit of commercial solar cell. So you are not you are not getting the entire spectrum available by the theoretical maximum. So you are getting a partial energy only. So now this pie chart and this left side shows the shares by various losses. So this pink one main loss is coming from the recombination and the resistive loss, which comes under the electrical loss. So that we will not consider at present. But the optical loss almost like contributes around 33%, which means that we can do still further reduce this optical loss by adopting suitable metallization strategies. So now the pie chart, which is this, which has quantified in terms of the equivalent current density I have shown here. So which shows that the front grid shading is a major phenomena which has to be reduced. So almost like 3.25 milliamps per centimeter square. So the contribution is slightly higher compared to the other contributions. So now let's see the how this optical losses generally occurs in the solar cells. So when incident light is falling on the solar cell surface, so several optical losses happens, as I told before. So the optical losses occurs since the incident photons can be lost through different loss mechanisms. So first loss mainly can be through the reflected or absorbed by the front contacts, that is called as a metal shading loss, or being reflected at the front surface of the silicon wafer. So that's a front surface reflection loss, or being lost due to the parasitic absorption in different material layers, or that do not actually generate the electron hole pairs. So that's called as a parasitic absorption loss. So then again, the fourth one being the reflected at the rear surface due to the weak absorption of the near band gap wavelengths and escaping after passing one or more times through the wafer. So that's front surface escape loss. So the metal shading is categorized as the optical loss of the inactive area, basically. So where no current is directly generated, then this loss also can be reduced by if you reduce the coverage of the fraction of the metal finger and the bus bars via adopting some advanced metallization technologies. So we will come to that point shortly. Then the surface texture also not only reduce the front surface reflection, but also contributes significantly to the light trapping. So by coupling the light into solar cells under an oblique angle. So because of the internal scattering at the interfaces, so some photons make multiple passes before escaping from the solar cell. So two types of texturing has been adopted by the industries. So first one is a pyramid texturing. So pyramid-like textures will be created throughout the surface of the solar cell. So that will enhance the absorption of the photons or minimize the reflection loss. Then some other cases like polycrystalline solar cells and all, isotexturing also will be adopted. So that also will reduce considerable reflection losses. So in little more in detail, if you have a closer look into the device structure. So not only the reasons which I told just now. So some more additions are there. So first one is a reflection or shading at the screen printed front contact, metal contact. So that's a metallization. So that's a shadow loss basically. So the reflection at the cell front surface. Then third contribution is from the reflection from the rear side out of the cell. Then the absorption in the front passivation and anti-reflection coating layers. Then the fifth point contribution will be from the absorption of absorption via free carrier absorption in the P type emitter layer. Then absorption via free carrier absorption in the N-type back surface field layer. The seventh contribution will be the absorption in the rear passivation layers, absorption in the screen printed rear metal contact, and transmission without being absorbed from the cell. So that's the parasitic cells, parasitic reflection. So different mechanisms exist as we discussed right now. So different contributions from different parts of the device is observed. So now if you see the metal fingers, so the direct reflection from the metallization pattern can also influence this such type of optical losses. This direct reflection from the metallization pattern and also the indirect reflection from the glass air interface on silicon surface. So if you see this particular figure, you can see that it has got different geometries. So the first one from the left, so typically it's a plated, electroplated contact. So that has got a different type of reflection losses. Then the second one is an advanced plated contact. So that one actually, if you see, can reduce the reflection loss considerably. But it's still under because several other challenges has to be crossed. So you need advanced metallization technologies in order to fabricate such kind of contacts. And the third one is the generally observed screen printed silver contact. So that also has got many disadvantages. As you see, there are several reflection loss happening in this case also. So you need some kind of advanced geometries, or you need some high aspect ratio features. So we'll see how such kind of metallization can be fabricated in later slides. So now we have understood about the silicon solar cell. So now let's see what happens. How can you make the solar PV module from these solar cells? So PV modules, sometimes you also call them as the PV as such, or solar panel. So this is a packaged assembly of many interconnected solar cells. So the silicon wafer solar cells are initially interconnected by the metal ribbons into series or parallelly connected strings, and then this solar cell assembly is encapsulated using a solar cover glass and a backsheet. Then this interconnection increases the voltage or and current, and also resulting in the enhancement in the power output. So the encapsulation basically protects the solar cells and the interconnects from the harsh outdoor environment, and throughout the modules, because it has to be protected throughout the it's a technical lifetime. Like for example, the solar cells are reported to be having a lifetime of around 20, 25 or 30 years. So throughout this technical lifetime period, it has to be protected from the outdoor environments. So that is the main purpose of this encapsulation. So the main aim of this particular encapsulation step is to interconnect the solar cells by soldering and packaging them into a weatherproof structure. So this particular step offers both electrical isolation as well as the protection from the environmental damage in which they operate, such like, for example, the moisture, rain, snow, dust, or some kind of a mechanical shock. So the most important stage of this particular encapsulation is the thermal treatment of the thermosensitive polymer resin. We call it as EVA. So EVA is nothing but ethylene vinyl acetate. It's a polymer. So the electrically connected cells are sandwiched between two EVA sheets. You can see from this figure. It's called as encapsulant EVA. So the solar cell is sandwiched between two EVA sheets, and on the other side, the front side, you have your tempered glass. So that's a solar cell solar cover glass, and back side you have a multi-layer back sheet. During this lamination process, the encapsulation happens, and this EVA act as a glue which encapsulate this solar cell into as an electrically isolated as well as environmentally protected structure. So that's basically the lamination, and after that it will be cured. So that's the basic PV module manufacturing process. So when you see this solar cell structure, you have several ribbons. Then the frame is there. After encapsulation process, then the it will be assembled in using the aluminum frame. Then if you have a closer look, so these are the metal fingers, and the blue region is the active region, and this white region which is shown in this figure is the back sheet, and the other one is the ribbons. So that's the basic structure of the PV module. So now let's see the. Yeah, we have seen the basic optical losses in the case of a solar cell, but once it is manufactured, assembled as a solar PV module, then you have to consider several other type of contributions towards optical losses also. Like for example, the solar cover glass which is used, so that also will contribute towards the reflection loss. And the glass also can contribute towards the parasitic absorption loss. So I have shown some numbers. So these are the different type of losses corresponding to that. So the third one is the EVA. So the EVA parasitic absorption loss. But of course, these losses are kind of coming from the active areas, which means that exposed silicon area. And this red highlighted ones, like the shading loss of metal fingers, the cell gap of photon loss, shading loss from the interconnections and ribbons. So these three losses are basically coming from the inactive areas, like metal fingers, ribbons, or backsheet, or the frame. So from that also the optical losses can happen. So that's the inactive area. Then further, the front surface IRC reflection loss, parasitic absorption loss in the cells, and front surface escape loss. So that's the active areas again, that's related to your solar cell, which we have already discussed earlier. So now the most significant loss is the photon loss. If you consider the different contributions of optical losses in the PV module, you can see that in this chart, you can see that the most significant loss is the photon loss at the back sheet. Then even after considering the lateral harvesting from the conventional wide diffuse back sheet. Therefore, in order to improve the output power of a PV module, so it is important to optimize the lateral photon harvesting from these areas also. So now it's something which is interesting I want to show you is that finger effective coverage. So that is actually contributing around 4.2%. So that is something related to our metallization. So we will see how to reduce the finger effective coverage. So now let's see what is the front contact grid. metal grid pattern. So if you see the front contact metallization of a silicon solar cell, if you have a closer look at it, you can see that several narrow finger line widths are printed on the surface as a front contact, which is actually interconnected by several bus bars. So the fingers, the metal fingers collect the current from the emitter side, and the bus bar collects from the finger lines and transmit them to the external loads. So now if you see the front contact metal set as a schematic diagram I have shown here. So there are some parameters which are very important. So one is finger spacing. So this inter finger spacing. So that is something which actually we can play around, or we can optimize it in order to improve the efficiency of a solar cell. And the second parameter is the aspect ratio of the this kind of fingers. So aspect ratio is nothing but the height, the ratio between height and width of this finger lines. So if you can increase the aspect ratio of the finger lines, again that is a kind of advantage for increasing it, advantage towards increasing performance of the solar cell. So now if you see, if you consider the front contact metal grid pattern, so you need to consider two basic parameters. Like first one is the grid resistance. So grid resistance, basically it is determined by the resistivity of the metal used to make the metal contact. Generally silver is used. Then the pattern of the metallization, and also the aspect ratio of the metallization scheme. And if you use a low resistivity and a high aspect ratio features, that is highly desirable for the solar cells. But again, if you see the practical limitations, because the technologies are not so much advanced to make such kind of a narrow finger width and very high aspect ratio features, although it is highly advantageous towards increasing the efficiency of the solar cell. But research is going on towards that. I also will present some important work which we did in our institute at the end. So then the second parameter is the shading loss. So already we have mentioned that the metallization, the front contact metallization contributes majorly towards the shading loss. So this is basically caused by the presence of the metal on the top surface of the solar cell, which is the fraction of the top surface covered by metal, which prevents the light from entering the solar cell. The shading loss basically is determined by the transparency of the top surface. The transparency is determined by the width of the metal lines on the surface and the spacing of the metal lines. So that already I have mentioned about that. And again, an important practical limitation is the minimum line width associated with the particular metallization technology. Because currently screen printing is used, so but screen printing, although it is a mature technology, it has its own limitations. Like for example, it can print at present latest technologies, like it can print almost 30 micrometer line width. But still, if they try to reduce the finger width, again the finger breaks or interruptions happens, and the technology is not a successful technology at this end. So a narrow metal line width, closer finger spacing, of course it can reduce the emitter resistance loss also. So that's the basic idea of this front contact metal grid pattern. So now let's see the overall, the top surface of this solar cell. So metallization, as I told before, that there are several metal line fingers which actually collect the current from the emitter. And then there are some bus bars which are interconnected vertically, crossing all these metal lines. So that actually transmits the current towards the external load. Now, if you see this particular figure, so this shows the various major components of the series resistance in the screen printed or any other printed front contact of the solar cell. So you can see that there are again the series resistance increases from contributions of the sheet resistance of p-type emitter layer that is mentioned as the E emitter, and the N back surface field layer, then the bulk resistance of N-type wafer, that's contribution from the substrate, then the metallic resistance of the front grid line and the rear grid line, then the contact resistance between the screen printed metal contacts and the silicon on the front side and the rear side also. Then the fifth contribution is from the metallic resistance of the front bus bar and the rear bus bar. So all these kind of different types of resistance are contributing towards the series resistance in front contact metal lines. So we need to reduce such kind of resistance also. So now let's see like the cost reduction which has happened in crystalline silicon solar cell, which means the cost per watt in 2017 to 18. In that period, approximately the cost of solar, cost per watt was 54 to or 45 range. So that was rupees. That was a range. So at present, if you see in 2020, that cost per watt has been reduced drastically, almost like half, like 24 to 40. So that's a kind of a range what we are observing right now in our country. So what does it mean is that although there are not much of advances has happened in the silicon solar cell structure, or design of the solar cell has not changed, but there are many advances has happened in terms of the cost reduction. So typically the major cost during the cell processing is coming from the metallization. Almost like 40% of the cell processing is contributed by the expensive silver paste, which are used for a metallization process. So if you can reduce somehow the kind of quantity of metal paste which are used for metallization, you can also considerably reduce the price of the solar cell. So that's the beauty of this particular area. So like by 2050, our target is like to create around 200 gigawatts. That's a target set by the National Solar Mission. Okay, so now you can also observe, although we can observe a rapid decline in the cost per watt. So that's how the solar installations are encouraged right now, and it has promoted increased deployment. And the cell processing, as I told, the 40% is contributed by the metallization. So if you can reduce the mass of silver required in the front grid, so you can reduce the cost of the solar cell also. So if you see this equation, the mass of silver required for the front grid is inversely proportional to the denominator, if you see. So that is the acceptable fractional resistive loss due to the front side metallization. Irrespective of the finger design, this particular equation shows that as the mass is reduced again, then the fractional resistive losses also will be increased. So somehow you should have a kind of optimal design for the metallization pattern to reduce the, either you should go for a less silver technology, or you should go for an alternative metallization. So, as an alternative to the reduction of, as an alternative to the reduction of silver consumption at the cell manufacturing level, so silver should be replaced on a large scale basis by more effective materials, basically. So alternatives are like, if you consider copper, so that's a very good substitute. But copper, of course, has its own disadvantages that we will discuss. But we can also improve that challenge we can actually face. So that I will show you later how copper can be used as an alternative. So the delay, the delay in introduction of copper into mass production is due to several reasons. So again, you need to face many other technical challenges and reliability and addition. So there are so many other challenges which has to be resolved. So then only the solar cell manufacturing technology will accept this particular technology widely as an alternative for screen printing of the silver paste. So again, appropriate equipment and process are required. Then screen printing. If you see this second chart, if you see the screen printing again, it will remain as a widespread metallization technology for some more time. But of course, the plating technologies and other concepts will be evolving gradually. So we can expect quite a lot of advances in terms of other alternative metallization technology compared to replacing the screen printing technology. So now we'll see the factors which are influencing the cell efficiency and the metallization cost. So efficiency basically can be improved by either by improving the current density, or you have to improve the fill factor. So current density can be improved by decreasing the finger widths for reduced shadow loss. So that's something very interesting for us. Then the second one is how to improve the fill factor. So that's basically by reducing the contact resistivity and reducing the line resistance, and of course improving the aspect ratio. So aspect ratio improvement is a little bit challenging, but if you adopt appropriate technologies, that is actually possible. So you can you can reduce the finger width, as well as you can also increase the aspect ratio. So thereby you can actually contribute majorly for the efficiency enhancement. Then considering the cost, how can you reduce? You have to either replace silver screen printing. Silver screen printing, if you are reducing, then you may tell that the cell performance is affected and the other technologies are not so matured. So you can also think of a less silver process. You can reduce the consumption of the silver by adopting. There are many methods which can be used to reduce the silver usage. What you have to do? Alternative metallization. Alternative metallization means you have to use comparable metallization without compromising the conductivity, but at the same time the cost of the metal should be very low. So obviously we will look towards the copper only. So before going to that alternative metallization, I just want to show you some glimpses of the technologies which are used for metallization of silicon solar cell. So before mentioning, because all of you know that screen printing is a major technology. So we'll discuss little detail about the screen printing, but before that I want to tell you the glimpses of alternative printing technologies which are used for solar cell front contact metallization. So first one is inkjet printing. So inkjet printing, all of you, I think most of you must be familiar with. In this particular technology, if you see the process flow, there's a continuous jet mode stream of ink, which is injected under high pressure through the nozzle. So this stream actually disintegrates into a train of droplets, and which is directed by the electrical signals. So the droplets which are not used will be diverted by the electric field and will be collected by a gutter, and it can be actually reused. Then the droplets which are ejected through the nozzle tip and will be directed on the surface using a piezo drive, electricity. You can actually have XYZ movement. So using which you can actually print the desired metallization pattern on the silicon solar cell. So in 2011, Xiong et al. Demonstrated an inkjet printed silicon solar cell and organic solar cell also. So control the drop flow in the deposition is very challenging in this particular process. So this may actually lead to the non-uniformity in the contact formation. And also the viscosity of the ink should be lower to be printable with the inkjet printer compared to the screen printer. So that will actually increase the line resistance. So the next process is the pad printing. So in this case, a photopolymer plate with the print image or the design will be etched into the surface. That will be mounted on the machine by means of a magnetic plate holder. So a blade spreads ink from the ink reservoir over the plate, filling the etched areas. In the next step, what happens is the doctor's blade. So that's a thin film technology. So that's basically the spreading of the ink. So this doctor's blade moves down and retracts the ink from the surface. And this ink will be left just in the etched areas only. Then after that, this solvents in the paste will be starting to evaporate, and the surface become a little bit tacky. So then after that, the pad moves downwards onto the plate and roll across its surface. So you can see that a roundish surface. So this rounded surface of the pad is important as this prevents air to be trapped between the pad and the plate surface. So when the pad moves upwards, some of the ink sticks to the surface. So at this point, some of the solvents evaporate from the surface of the paste, which adheres to the pad, making this surface a little bit sticky. Then the plate is moved away from the pad and moves downwards onto the substrate. So at that time, the ink sticks onto the surface of the wafer and will be released from the pad as the pad lift upwards. So that's the main process flow which is adopted in pad printing. So, although there are some reports on this pad printing, so again, the line resistivity is increased due to the low paste transfer. Then during firing process of pad printed cells leads to lower fill factor. So obviously, if the fill factor is lower, you can expect that the performance of the solar cell was not so very good. So that was not kind of widely accepted technology because of that. And the next technology is that aerosol jet printing. So in aerosol jet printing, there is a metal aerosol jet printer, which is a non-contact system. So this allows printing on thin and fragile wafers. So at present, if you see the silicon solar cell, you can see that most of the silicon solar cells are very fragile and it's very thin. So for such kind of wafers, this technology will be advantageous, of course. And it can also print on wafers having uneven surface. Then this aerosol, in this case, aerosol is transported to the deposition head via heatable tube, where the viscosity of the aerosol can be controlled. So one most important component of the ink for solar cell metallization is metal loading in the form of nanoparticle ink. So nickel, chromium, titanium, etc. could be the materials of first choice for contact layer. So again, in this case also, although this technology is very good for making a narrow line width features, like up to around 15 micrometers feature size can be obtained very easily using this aerosol jet printing. But the problem is that the aerosol ink, the nano ink, which is used to produce aerosol, is expensive, and also the technology, overall technologies are going to be costly for large area industrial manufacturing. So that's why this technology also was not so very successful, although it has got some good advantages. So the next process is the co-extrusion printing. So in this case, the co-extrusion print head consists of a multi-layer nozzle assembly clamped between two sealing plate structures. Then a manifold plate distributes and splits two extrusion materials, a silver gridland paste and a kind of sacrificial paste are used. So again, in this case also, you can create a high aspect ratio features very easily. So once the line is deposited over the wafer, the sacrificial paste prevents the lateral spreading of the metal paste. So that actually enables the aspect ratio. So this technology also is very good to create high aspect ratio metal lines. But again, the problem is the cost for wider deployment. So next important technology is the laser micro-sintering. So in laser micro-sintering, so this is basically a rapid prototype technology. So this is used to create three-dimensional objects by layer approach. So in this case, a laser will be applied to fuse a thin layer of the powder material spread on the solid object. So you can see in this schematics. So metal powder will be spread on the wafer, and the laser will be falling on the surface. So this laser beam basically with appropriate energy scans over this particular powder bed. So the metal powder, basically it is sintered and bonded to the emitter surface. So the main challenge for solar cell metallization is the investigation of laser processing parameters. So applying enough energy for powder fusing and bonding to the cell surface without damaging the thin, preferably the doped emitter surface. So it should not be destroyed, but at the same time, you can get high aspect ratio as well as narrow line width metallization using this particular technology. But again, the processing parameters are very complex. So that's why the technology was not so very popular. And the next important technology is the photolithography. So whatever in the internal chart you are seeing many high efficiency silicon solar cells. So those kind of high efficiency has been actually achieved by the adopting photolithography technique. So I think some of you must be aware of the what is meant by photolithography. So in this case, you need a photoresist, and the UV light will be exposed to the UV light with a desired photo mask. Some of the part of the photoresist will be hardened, and the other one you can etch it out using wet etching or some other physical etching process. And then you can evaporate your metal, and after that you can wash out your whatever resin which is residual present as a residual material. So using this particular technology, this is highly very precise method for the metallization, but unfortunately there are several steps involved, as well as you need expensive clean room microfabrication facilities for this. So that's how if you adopt this technology for commercial solar cell manufacturing, again the cost of the solar cell will be very high. So that's one disadvantage for this particular technology. So now let's come to our main technology, that is a silver screen printing of metal contact grid lines. So during this screen printing process, actually you are using a screen with some openings of your corresponding to the design of your metallization pattern, and the silver paste will be placed on this screen. You can see the screen over here. That's a mesh screen, and there are some openings. So that corresponds to the metallization space. And the silver paste will be placed on this particular screen, and there will be a squeegee which will push this metallic paste throughout this mesh screen. So what happens through this opening, this metal paste will be pushed into the solar cell wafer. So that's how you will get the patterns on the solar cell surface. And then after that, this metallization, the screen will be lifted out, and then drying process will be occurring, and after that one more sintering process will be occurring, so which will assist adhering this metal lines onto the emitter surface. So that's a screen printing process. So this particular photograph shows the screen printed silver fingers as well as the bus bars printed through screen printing technology in the commercial production scale. So now, if you see the process flow adopted for screen printing for solar cell front contact, so I don't want to explain all this texturing, diffusion and all again. So in this case, the silver paste. So the silver paste contains also aluminium. So so before that, what happens? This aluminium and silver based silver paste will be screen printed, and then during firing, this silicon nitride will open up, and then these metal lines will be in direct contact with the emitter layer. So that's how you get very good adhesion, as well as the conduction happens very efficiently. So now during this sintering process, so initially drying process will be happening. So where this solvent burnout, because the silver paste basically contains both inorganic and organic materials. So inorganics are like there will be some glass flakes, then silver powder will be there, and there will be some polymer additives. And organic matter will be like the solvent, because it has to be it has to maintain some kind of rheological properties. Some viscosity has to be optimal, and there will be a resin, and some additives will be as organic matter. So if you see this table, I have listed out the kind of composition which are used in silver and aluminum thick film paste. So the metal powders will be there. That could be the silver. As in the case of silver paste, silver will be the major contributor, like 70 to 85% will be the silver, and there will be some glass flakes or binder materials will be there. They are the ethyl cellulose, PVA, methyl methacrylate, etc. Then there will be some carrier materials. So that means that a solvent is required. So solvent will be there. They are the wetting agents, and it also assists in controlling the flow. So then now after this drying process, then the next stage, if you increase the temperature up to 200 to 400 degrees Celsius, the volatile matter burns out. Then after that, again, they will increase up to 600 degrees Celsius. So at that time, non-volatile matter will be burnt out. Then after that, up to 850 degrees Celsius, they will sinter. So during this time, the metal starts to sinter and the glass fits. So there is a glass materials are there. So that glass flows through these voids. So that can actually assist the addition of the metal lines. So now this is what I told, the silver or aluminium. So silver, if aluminium is present, some amount of aluminium also will be present, and the glass material will be there. So they will actually form some kind of a bimetallic species, and they start to etch out this silicon nitride at its contact, and through that opening, it will be in direct contact with the emitter. Then the contact also should not be, because the silicon nitride is almost like the thickness will be around 70 nanometer. It should actually etch out the silicon nitride to have a proper contact, but again it should not over etch, because again it will disrupt the overall process. So there could be some kind of optimal temperature is there for sintering process. So using screen printing, you can see that up to 35 micrometer width finger lines has been printed at this point of time by latest screen printing technology. So again, advancements are happening. So if they are able to reduce again the finger width and aspect ratio, then the technology is okay, good. But still, if you are thinking about the cost reduction, you definitely require an alternative metallization process. So during this screen printing process, the agglomeration of silver particles has been observed. Again, the screen opening should be 5 times larger than the particle size. So therefore, the silver particle size should be in the range of 3 to 7 micrometers. The finger opening above 35 micrometers to avoid screen clogging is required. So that's one disadvantage, because when you go for narrow line width, again the silver particle size should be another challenge to reduce. So that is something you have to think about. Then another disadvantages are like non-uniformity in the fingers. So if the lines which are printed are non-uniform, that will increase the shear stress, and again that will increase the resistivity of the finger. And as you reduce the dimension, as you reduce the finger width, again the possibility to have finger interruptions or finger breaks will be enormous. So that is another challenge which has to be thought about. Then again, such kind of non-uniform fingers, it will increase the series resistance. So these are some of the disadvantages of screen printing of silver paste. And again, as alternative front contact metallization, some groups have reported TCO, transparent conducting oxide, because in that case, it's a transparent conductor. So obviously, you can expect that the kind of loss, the shading loss can be reduced. So, but again, the technology which they were using was photolithography. So the printing is very difficult in that case. So the cost was very high in that case, although the efficiency was very high. Then the world's highest efficiency was actually made by the expensive lithography process. So multi-metal was evaporated as stacks like titanium, palladium, silver. But you see, those other materials also are very expensive. Palladium is very costly. compared to silver. So that technology also was not so very successful. The current scenario is that there are several printing metallization techniques like screen printing, inkjet printing, aerosol printing. Then two techniques which I have not mentioned is nanoimprint lithography and maskless lithography. So that technology actually we have developed in our laboratory. So that I will discuss about that sometime later. So such technologies also has got silver usage is very low, or you can also go for silver-less process using nanoimprint lithography and maskless lithography. Efficiency is very high, which we have already proven in our laboratory. Printing accuracy is very high. High aspect ratio features can be printed. Then fabrication cost is low for nanoimprint lithography, but for maskless lithography, it was found to be a little bit moderate. And it's both are high throughput technologies. So now let's see. A second. Yeah. So now I have shown two schematics here as to describe you what is meant by this alternative metallization. So in the first case, first schematics, the picture A. So you can see that two screen printed silver contacts are printed on the surface of silicon solar cell. Then in the second case, what I have considered is there is a kind of a difference in this metallization. It's a less silver process. So I have got a nickel contact over here as a seed layer, and the main conductor is going to be the copper contact, and on the top of that I have a AG capping layer. So this is one of the alternative metallization process which can be considered. So in this case, the silver usage is going to be very less, but at the same time you have a kind of complementary conductor, like almost like conductivity. If you compare the silver, copper and nickel, the conductivity is going to be comparable. Silver conductivity is almost like 61.39, and copper is very close, 59.10. So there is no significant decrease in the conductivity. Both are almost like comparable. So you can actually use copper in the place of silver. But the problem is that the copper, if you use as a metallization, the metallization grade, there is a possibility that copper diffuse into the silicon. So diffused copper at the junction, it increases the leakage current. And also it can act as a deep level impurity and form traps, which can reduce the carrier lifetime. So what you need is not directly deposit copper on the surface of the solar cell. You need a seed layer, which is nickel. You can consider nickel as a seed layer that will actually increase the addition as well as increase the conductivity. So nickel, while sintering, it will form nickel silicide at the interface of this silicon and the nickel. So that will actually assist improving the addition as well as the conductivity of the metal lines. So in that way, you can prevent or block the diffusion of the copper into the solar cell silicon the silicon interface emitter surface. So that's how there's an advantage. There's a very good future we can see in terms of copper if you use it as a nickel copper contact. So if you see this cost also, cost is like there is a huge variation between silver, because you already know that silver and gold price is going like anything, increasing like anything. So at some point of time, we don't know where this will go and end up. So if you see the copper and silver cost, there is a huge variation, almost like 880 to $6.5 per kg. So that's a kind of difference in cost is observed, and nickel also is not so very costly. So that's a huge, like we can see that this can be actually considered as a good alternative metallization for solar cells. So if you see the alternative metallization, like nickel copper contacts itself, like in the previous slide, I have used silver, but you need not consider silver. If you are going for a silver-less process, the purpose of silver or tin in this case is it only acts as a capping layer. So that will prevent the oxidation of the copper and it protects the metallic fingers. So that's the purpose of using the capping layer. So first stage is the nickel seed layer deposition. So you can use either electrolyte deposition or light-induced deposition or laser-assisted deposition. There are many methods for nickel deposition. So you need a maximum of 100 nanometers of nickel seed layer or less than that. And after that, you need a sintering process because you need to produce this nickel silicide. So nickel silicide formation is in the range of 300 to 400 degrees Celsius. And after that, your actual conductor, the copper electroplating can be done. So that can be done using, generally electroplating will be adopted, or there are many latest technologies like light-induced plating or electroless plating. There are many methods. And I prefer electroplating for copper. And the fourth one is silver or tin. Silver is not necessary because the purpose is only to prevent the oxidation of copper. So we can prefer tin plating as a capping layer. So that completes the your whatever metallization. So in this schematic, you can see that before, the nickel seed layer will be deposited. So before that, you need to open up your ARC layer. So ARC layer is a silicon nitride layer. So that silicon nitride layer can be opened up through wet etching using some patterning. Like you can do some patterning over that, and then wet etching can be adopted, or you can use reactive ion etching. There are many methods to do the patterning of your opening up the ARC layer. So because you need direct contact between the metal and your emitter layer. So nickel seed layer will be deposited in these openings of this ARC layer as per your design pattern. And then after that, your sintering happens, and then the copper will be plated, electroplated, and over the nickel seed layer. And after that, your capping layer, like silver or tin capping layer, can be deposited. So that's basically the metallization steps which are involved in this particular alternative metallization. So nickel can be deposited using electroless plating, which is very simple. Basically, this electroless plating, it's a kind of autocatalytic process. So in which the plating can take place on an activated substrate. You need activation of your substrate without the need of the electrodes or current flow. You don't unlike electroplating, you don't have to give some kind of voltage into this electroless plating. So electroless deposition actually involves a reduction of the metal cations by electrons obtained from the reducing agent. So if you see the electroless plating bath composition, so there is a source for nickel, that is nickel sulfate or nickel chloride can be used as a source for nickel. And there is a reducing agent. So that's the basic, normally you can use sodium hypophosphite. And next, a buffer or a mild complex agent will be used to control the plating rate. So a chemical reaction, I'm a chemist, so I will be interested to see these equations, but I don't think most of you will be chemists, so I don't know how interesting it will be for you. It's electrochemistry. So there are oxidation and the reduction happens, and the hypophosphite dissociate into the hydrogen radicals, and then it will react with the OH minus. Then this hydrogen, there will be an hydrogen evolution also. occurring because this hydrogen radicals will combine to form hydrogen. So during these reactions, hydrogen evolution also will be occurring. So basically, the reducing agent undergo oxidation, producing, you can see in this schematics the general equation. So the reducing agent undergo oxidation, so producing some electrons. So that electrons will be utilized, and these electrons will be given to your substrate, which is activated already. So the metal precursor ions, in the case of nickel, nickel 2 plus. So nickel 2 plus will diffuse towards this your activated surface, and the electrons which are deposited by your reducing agent will be taken away by this nickel, and it will be reduced into nickel, metallic nickel. So that's how the deposition happens. That's nickel electrolysis plating, seed layer deposition. So after that, you will have already I have explained this process flow. You using some photoresist or some any like an imprinting, nano imprinting. I will be explaining. So how to open up this ARC we'll see later. So some using some wet etching or reactive ion etching, dry etching, you can remove your silicon nitride, and after that your plate electrolysis nickel plating will happen. Then after that, your next target is to deposit the actual conductor. So that's a copper electroplating. So initially, after electrolysis plating of nickel, you need a sintering process. I already told that nickel silicide has to be formed. So a nickel silicide at almost like a temperature of 300 to 400 degrees Celsius. After that, you need to deposit a copper. So copper generally will be electroplated as a front conduct. So in this case, copper sulfate along with the copper anode is commonly used for electroplating of copper. So due to the, you need to apply some electric field. So due to the applied electric field, the positive charged ions will migrate towards the cathode, while negatively charged ions will move towards the anode. So you know that the reduction happens at the cathode side. The cathode side is your wafer. So you will have the deposition of copper on the surface of the nickel, because other sides are masked by the photoresist. So the deposition happens only on the patterned lines. So copper will be reduced into metallic copper. So in this picture, I have just for your understanding. So you can see that there are some colors. So this is basically EDS mapping done by some SCM. So you can see that the nickel is there as blue, then copper, then they have used silver. You can also use tin for encapsulation. So this looks like the structure will be looking like this. So now, do I have time? Some more, Dr. Diban Raj? Can I?
Ma'am, it's already 11 is going to be. So you can take some 5 or 10 minutes if needed.
Okay, fine. Okay, so now I will little glimpses of our work I will be explaining. So we also work on this development of alternative metallization scheme based on nickel copper tin combination. So we have already optimized the nickel copper tin metallization process in our institute. Using our facilities, and it was done as a part of DST project. So you already we have optimized the process, but the thing is that you need also the metallization design. The patterning has to be done. So for that we have to use micro nano patterning. So we have adopted nano imprint lithography and maskless lithography for advanced micro patterning of this metallization. So before that we have carried out some simulations. We actually used gridless simulation for the simulation for the metallization grid. So because we need to optimize the finger width, the interfinger gap, and the aspect ratio of all those things. So we need to use some simulation package. So the Gridler is a simulation package which we used. So we did finite element analysis based simulations for this purpose. So this Gridler simulation actually gives you higher accuracy in measuring and generating nodes. And also we can use the commercial solar cell conditions in this case during this simulations. So different metallization patterns also can be adopted. So initially we try to do the optimization of the finger width. So as you see in this figure, you can see that almost like 10 to 80 micrometer different types of finger width we have optimized and found out its shading loss in terms of percentage. So we have found that almost 7.85 to 3.43 percentage has been varied as you go down the finger width. So from this we can understand that the as you decrease the finger width, the shading loss can be decreased. So that is quite obvious. We also know that, and so we tried to do the efficiency calculation in terms of a number of fingers. So if you reduce the number of fingers, then finger width, you need to increase the number of fingers. So for 10 micrometer fingers, we found that almost like 300 fingers are required to achieve some efficiency of 20.1. But unfortunately, if you increase the number of fingers like this, 300 lines means of 10 micrometer, there are processing challenges are there. And you can expect that several finger breaks may be there. So you have to avoid that kind of a reduced dimension. So then further we also checked the 20 micrometer finger width. So for which we have we compared the efficiency to the commercial solar cell finger width, that is a 60 micrometer finger width with 80 number of finger lines for commercial solar cells. Whereas for our solar cell, it was 20 micrometer finger width with 160 number of fingers. So we could see that there is a change in efficiency which we could see. Compared to commercial solar cell, there is a increase in efficiency, almost like a 1% improvement has been observed in terms of efficiency. So then we also calculated the sheet resistance based on simulations. So the total power loss was calculated as less than 2%. And we also optimized the interfinger distance, which was found to be 1000 micrometers. Then I will quickly go through. Then we also optimized the number of fingers for 20 micrometer line width. So which from which we understood that the finger width with the 20 micrometer with 160 number of fingers could show the enhanced fill factor as well as enhanced efficiency. So now the optimal dimensions are like the line width is 20 micrometer, interfinger distance is 1000 micrometer. So then for patterning, the experimental side, when you see, we used both NIL. NIL is a nano-imprinted lithography. So since time is not there, I will not explain this in detail. So we have two types of NIL process. One is a thermal NIL and a UV NIL. So in the thermal NIL, there will be a resist coating and there will be a imprinting mold, which we have to fabricate ourselves according to our design. And then there will be a thermoplastic or a polymer resist. You can either use a polymer or a photoresist on the surface of the substrate silicon wafer. So then you will be bringing down this imprint mold towards your polymer or polymer resist film, and heat will be applied. So because the polymer has to be little bit soft to have a proper molding or the stamping process. So we bring the temperature near to the glass transition temperature of the polymer basically. And then after that, after cooling, we'll separate the mold. So the desired patterns will be imprinted on the polymer resist. So that's how you do the thermal NIL. So in the case of UV NIL, instead of the after resist coating, you expose this film to UV light for curing. So you don't require any further cooling into that. But in our case, we have used thermal NIL. So if you see nano imprint lithography, if you see in high-end laboratories, it's very expensive tool, which cost in crores. So that very costly technology we have designed and manufactured, fabricated in our own laboratory. This may cost only one costly component is the actuator. So that comes around 4 to 5 lakhs. So the total cost is around 7 lakhs. We can actually manufacture this nano imprint lithography tool. So if any of you require this imprinting tool to be purchased, you can actually purchase from us. We can make it actually. So this is the imprinted lines, optical micrographs of the imprinted lines. You can see that 20 micrometer features has been very successfully imprinted on these patterns. So we have also published a paper based on that. You can see details from that paper. So this is how we did the metallization afterwards. This first figure is the silicon solar cell without metallization. You can see only silicon nitride here. After that, we did the patterning using either nano imprint lithography or maskless lithography. That maskless lithography also is available in our institute. So if you want, you can approach us. Then after that, silicon nitride was etched, and then nickel electrolysis deposition was carried out. And after sintering, copper was lithoplated, and after that, tin encapsulation layer was fabricated. So final outcome is like this: bare solar cell without metallization we got from the industry because we had a collaborator in Adani Solar. So he supplied us this bare solar cell. Then after that, we did the electroplating, copper electroplating, and tin electroplating was carried out. So now at present, I have not shown those data. So now we have also calculated the solar cell efficiency, and it was actually matching with our theoretical predictions. Almost like improvement in the efficiency was obtained. We got around 18% efficiency with our alternative metallization process. So which means that it is a very efficient technology. So it's a industrial ready process right now. So my research scholar has completed a PhD with this work, and he's actually about to submit his thesis right now. And this is our paper, and some more additional papers are in communication right now. So you can, if you want to see more about our work, you can actually go through these papers. So this is my group. Like half of the students are working in sensors, and half of the students are working in various aspects of clean energy. So thank you very much. So if you have any questions, I can answer.
Thank you very much for the wonderful session, ma'am. Participants, you can ask your questions now, either through madam directly or through the chat box. No questions?
Was it a little bit heavy or lighter? I don't know.
Okay. Thank you very much for the wonderful session, ma'am. Really, it was very interesting because most of the persons here are from mechanical background, and also few from chemistry and chemical engineering.
Okay, right. I'm a chemist turned into a engineering science. So can actually understand a little bit of both, so no problem.
So here for the past few sessions, we had gone through the solar concentrators, thermal collectors, heat pumps, hair heaters like that with the CFD applications and all. Really, this session is somewhat different to us, and we learned some new concepts related to the solar cells.
Yeah.
So thank you very much for the wonderful session, and we are very much grateful to you to be here for this session in spite of your busy schedule. I heard that you are very busy with a lot of funded projects and guiding the research scholars in addition to your regular teaching activities. But you accepted our request and you graced the occasion with your presence. So on behalf of Jyoti Engineering College as well as ACT ATAL Academy, my heartfelt gratitude to you, ma'am. Thank you.
Yeah, thank you very much for the invitation and the opportunity given. And we can interact more later sometime. And I will be happy to deliver some lectures at some other time on a different topic.
Yeah, ma'am. Sure.
Thank you.
Thank you, ma'am.
Shall I sign out?
Yes, ma'am.
Yeah, thank you.